All right, so we have a sequence A1, A2, A3, and so forth. Let's define some terms that we're going to be using for the rest of the semester. The sum, the sum of the first n terms of the sequence. So what do I mean? Let's assume we're summing all the AKs. We're summing AKK running from 1 to capital N. So that's A1 plus A2 plus A3 all the way to AN, A1, A2, all the way to AN. All right. This is called the nth partial sum of our sequence. Sometimes this is denoted as Sn, right? So that would be Sn is just summation k from 1 AK to capital N. All right. Now we can talk about another type of sum, the sum. So instead of summing from k equals 1 to n, we sum from k from 1 to infinity of AK, A1 plus A2, A3, and so forth. This is called an infinite series. An infinite series resulting from the sequence. So infinite series partial sum. Now, a big part of our study would be to know when this series, when we can find the sum of an infinite series and when we can't find it. So if we can find the value of the infinite series AN, we say the series converges. Otherwise, we say it diverges. Otherwise, it diverges. All right. Okay. Convergence and divergence are two concepts we're going to be looking at, two related concepts. Now let's look at some examples. So let's look at the sequence. We have this sequence 1, 2, 3, 4, etc. A very simple sequence. So we know that the formula for this sequence, if you remember the last time we talked about explicit formula, would be that AK is just K, right? K going from 1 to infinity. So, all right. So that means that the series, the infinite series, let's talk about the infinite series. Would be summation k from 1 to infinity of just k. Okay? So we're summing 1, 2, 3, 4. So this is the same thing as just 1 plus 2 plus 3 plus 4 and so forth. Now, what does it converge? Does it diverge? This easily diverges, right? Because it just sums to infinity. It doesn't add up to a number. We'll get to a point where we do an example where it converges. Let's give an example of a partial sum. Example. How about if we sum k from 1 to 4, right? So this is just going to be 1 plus 2 plus 3 plus 4, and this is 10. So this is a partial sum. This is the fourth partial sum. Let's call it, we can say, an example. So let's do S4. S4 is k from 1 to 4, and this is 10. All right, let's do another example. Let's do example 2. How about we have a series or a sequence, and this sequence is sine of n pi. So let's simplify this sequence and see what it is. So this is sine of pi, sine of 2 pi, sine of 3 pi, and so forth. What is this sequence? What is sine of pi? This is actually a sequence of zeros. Sine of pi is 0, sine of 2 pi is 0, etc. They're all zeros. Okay. So, do we need to answer more questions? Well, let's talk about the infinite series. The infinite series, summation k from or n in this case, little n from 1 to infinity of sine of n pi. This is sine of pi plus sine of 2 pi plus sine of 3 pi, and so forth. But this happens to be all zeros. So this is equal to 0. So this is an infinite series that converges. It actually converges. Another one. Let's do the same thing but cosine. Cosine of k pi. Alright. So this is let's do this. This one goes from n equals 1 to infinity. We can start wherever we want. Let's start with 0 here. N equal to 0 to infinity. So in this case, we have cosine of 0, cosine of pi, cosine of 2 pi, cosine of 3 pi, and so forth. Now, this is cosine of 0 is 1, cosine of pi is -1, cosine of 2 pi is 1, cosine of 3 pi is -1, and so forth. Alright, so this is an interesting series, interesting sequence, which will lead to an interesting infinite series. So this is summation. We can go from k is equal to 0 to infinity of cosine of k pi. right? So this is gonna be cosine of 0, cosine of pi, plus cosine of 2 pi, etc. So this is 1 plus negative 1 plus 1 plus negative 1 and so forth. This actually diverges because it doesn't add up to anything. So think about it. It doesn't go to infinity, but it doesn't add up to anything. So if we do this first two, this would be 0, right? If we just do this, this would be 0. But if you go again and you now add this one, that will give you 1 and so forth. If you add this again, this will give you 0, and you keep going like that. So it's gonna add up to either 0 or 1. All right, so assuming it adds up to 1. But then if you do the next term is negative 1, so it becomes 0. So it oscillates, the sum oscillates between 0 and 1. Okay. So it diverges. It doesn't add up to a particular number. All right, let's do a series that is the building block of many series. So let's start with 1/2. This is a sequence. Consider the sequence. So this is a sequence. Let's go 1 over 2 to the power of k. So this is k from 1 to infinity. So this is 1/2 plus 1/4, 1/4, 1/8, and so forth. So this is just a sequence. Now let's talk about the series. The series is the summation this is the summation k from 1 to infinity of 1 over 2 to the power of k. So that means we're just adding 1/2 plus 1/4 plus 1/8, and we keep going. Now let's see if we can add this up. Okay, this is a very interesting series. So I'm gonna do this. I'm gonna use up a whole okay, I don't know how to do this. I want to draw a square, so that's all I want to do. You guys are probably confused. What is he doing? Oh no. Okay, I'm gonna do this, and then I'm gonna draw another one. No. Okay. All right, what am I trying to do? Make this a little thicker. Maybe this. All right, so this is one a square. Now I want to get 1/2. So let's assume this is 1. This square, its area is 1. I want 1/2. So this is 1/2. This will give me 1/2. Okay, so this region is 1/2. Clearly this is 1/2. Now 1/2. So I have my 1/2. I'm gonna add one fourth to it. This is 1/4. I'm gonna keep going. I'm gonna add 1/8 to it. So this is 1/8. You see what I'm doing? 1/2 plus 1/4 plus 1/8. So that's what we have here. So let's just keep going. The next will be 1/16. So let's add 1/16. All right. I'm going to shade it red. The next will be 1/32. All right. And then the next will be 1/64. Now, if we add all these areas up, it's going to sum up to 1. Because we're going to keep dividing and adding, dividing these little things. So we divide this one, and then we add it. So we've already added these ones. We already added this, but then we divide this one and add it. So at the end, it's just going to add up to 1. So that's my proof that this sum goes to 1. So this is proof by picture. It's not a very analytical proof, but it's acceptable. I can actually write it up and really explain it, and it will be a proof. So this series is called the geometric series. Okay? So we're going to spend a little time studying this series. So this is geometric sum. Talk about geometric sum, talk about geometric series. All right. So a geometric sum has the form summation k from 0 to n. Okay. So, mind you, we went from 1 to infinity. But here the way we're defining, we're going from 0. But it doesn't matter. And this is a r to the power of k. Okay. So this is just an example of a geometric series where the a is 1 and the r is 1/2. But we'll talk about that more. So a geometric sum has the form summation k from 0 to n of ar to the k, where a is not equal to 0 and r is a constant. So r is usually called the ratio. Okay, the geometric ratio. Let's look at examples. Examples number 1, summation k from 0 to infinity of 3 times 2 to the power of k. All right, so a here is 3 and r is 2. So we're going with this. A summation k from 0 to n of AR to the power of K. Okay. So before we move on, I'm going to add a little bit more to this definition. So I defined the sum. I'm gonna say the infinite series. The infinite series K from 0 to infinity, a times r to the power of K, is called a geometric series. Geometric sum is that geometric series. Okay, it should make sense by now. All right, or no? Okay. Now, how about, what did I just do? Okay. So how about summation K from 0 to 10 of 1/2 to the power of K? So in this case, our A, we know our R. Let's write our R first. R is 1/2. Our A is just 1. Because you can think of having an invisible 1 over here. Okay? Now, let's look for a formula for computing a geometric sum. So as you guys can tell, this is a geometric series. This is a geometric series. Because of this, right? And this is a geometric sum. Because of that. All right. So let's look for the formula of a geometric sum. The sum. This is actually very good. I like proving this. Sometimes I mess it up, but I like it. All right, let's start with a partial sum, right? This partial sum, let's say it's summation from K from 0 to n of a r to the power of K. When K is equal to 0, it's just A. When K is equal to 1, it's AR. When K is equal to 2, it's AR squared. And we keep going to the point A. We have AR, okay? To the power of N, I think. All right. So now let's assume we multiply our summation by R. So we have R as N. So this is summation. Let's just multiply by N. Let's not worry about writing the series. So this will just mean multiplying each of this by R, sorry. So this is A. Let's align it together. This is AR plus AR squared plus AR cubed. All the way to r to the power of n plus 1. Okay, now let's do some subtraction. Let's subtract these two things. So that is Sn minus Rsn. All right, that will give us, look at what's happening. If you look at this, you're subtracting this whole, the second line from the first line. So AR is gonna cancel out with this, because this would be AR minus AR. This is gonna cancel out with that, and so forth. This is gonna cancel out. This is actually gonna cancel out. So you'll be left with A minus AR to the power of n plus 1. All right. So let's see, what do we have? We have, let's factor out an Sn over here. We're left with 1 minus R. And then definitely we can factor out an A here. We're left with 1 minus R to the power of n plus 1. Now, think about where we're going. This is now telling us that the formula for the summation of a geometric series, this means that Sn is basically, well, let's not write it here, a little confusing. So this is just telling us, if you divide both sides by 1 minus R, you get that Sn is equal to A 1 minus R to the power of n plus 1 over 1 minus R. 1 minus R. Okay. Okay. So this is our formula. This is a formula that, well, let's not box this. This is the formula we want to get. So because Sn is just summation k from 0 to n of AR to the power of k. So this is A 1 minus R to the power of n plus 1 over 1 minus R. This is a very good formula. All right, let's do some examples. The first one, summation k from 0 to 4 of 3 to the power of k. So this is a geometric series. This is a geometric series with A 1 and R is 3. So we have a formula for a geometric series. So this summation is just we're gonna use our formula. We're gonna use A times 1 minus R to the power of n plus 1 over 1 minus R. And this is gonna be 1 times 1 minus 3 to the 5th over 1 minus 3. And this, when I did it, I got negative 242 over negative 2. So this is 121. That's what I got. Now, how about this? I want you to notice something. Notice the fact that this summation starts from 0. All right? So to use this formula, you have to make sure that your series, the summation of your series, starts from 0. If it doesn't start from 0, you can't use it. So let's do an example where it doesn't start from 0. So let's do summation k from 2 summation k from 2 to 4 of this same series. Now, in order to do this, we have to rewrite it to make sure it starts from 0. And then we subtract what we don't need. What do I mean? I'm going to rewrite this as the summation k from 0 to 4 of 3 to the k. All right, so we know that this doesn't, that this summation starts from 2, but let's make it start from 0. And then we're going to subtract the 0th term, the 0th term. So we're going to subtract the 0th term. We're going to subtract the first term, right? So we're going to subtract k is 0 all the way to k equals 1. Okay, so this k starts from 2, 2, 3, 4, right? But here we have 0, 2, 3, 4. So we don't need 0, we don't need 1. So we have to subtract 0 to 1. So assuming it's let's do a little exercise by the side in red. So assuming we have k from, we want k from say 10 to 35. Then that means we're going to go k from 0 to 35 minus, I'm just going to put a random series, a random something there, minus k 0 to 9, okay, because we want 10 to 35. All right, so I'm gonna cut this. So that's just a little example to make this more clear, to make this example more clear. So we can use our formula on each part of the sequence or of the series. So this is, we're going to use 1 minus 3 to the power of 5. We already have this, 1 minus 3. Mind you, we're using this formula, right? And then we're just going to subtract, we're going to do again 1 minus, our n in this case is 1. So 3 to the power of 1 plus 1, which is 2, all over 1 minus 3 again. So if you do this right, you're gonna get 121, and I think that is 4. So this is 117. Okay. Now, there is a common mistake that students make. The common mistake is not properly distinguishing between a partial sum and an infinite series. This is a partial sum. These are partial sums. It starts from k, from 2 and ends at 4. It starts at 0 and ends at 4, and so forth. If it ends at a number, at a tangible number, it's a partial sum. If it ends at infinity, is an infinite series. An infinite series can either diverge or converge, but a partial sum always converges. A partial sum always converges. A partial sum always converges. All right, so make sure you remember this. I'm going to write it down. An infinite series diverges or converges. A partial sum always converges, because it stops somewhere. It always converges. These are all partial sums. Now, we dealt with the formula for a geometric sum, right? Now, let's extend this formula to a geometric series, okay? So, an infinite geometric series. Infinite geometric series. Now, this is what it looks like. K from 0 to infinity of a r to the power of k. What I'm going to do is that I'm going to write it as a geometric sum. K from 1 to n, a r to the power of k. Right? This is not the same thing. N and infinity are not the same thing. But I'm going to let n go to infinity. Okay? The limit as n goes to infinity. Make it like this. So this is a limit as n goes to infinity of that. Now, we know the formula for a geometric sum. The formula is a 1 minus r to the power of n plus 1, right, over 1 minus r. So we're just taking the limit as n goes to infinity. Now look at this. Look at this. What does this look like? This looks like, let's think of numbers. Let's plug in numbers for r, okay? Let's write it this way. We can factor out, I'm very sorry, outside my house is very noisy, outside my apartment. So we can factor out the a. The a is a constant, so we're just dealing with this. We're just dealing with 1 minus r to the power of n plus 1 over 1 minus r. Think of what this fraction looks like for different values of r. Let's start with r is equal to 0. If r is equal to 0, then we're good. This particular series, this particular fraction will just be 1. So that's an easy one. But now think about when r is equal to 1, for instance. If r is equal to 1, what do we have? We have 0 over 0, which is undefined. Okay? So we're beginning to figure out where this breaks down. So at 1, it's undefined. So let's look at the right of 1 and the left of 1. Okay? So let's look at when r is less than 1. If r is less than 1, if you look at what happens to this if r is less than 1. If r is less than 1, as n goes to infinity, you're raising a number that's less than 1 to a really high exponent. So this whole thing will go to 0. It will go to 0 if it's less than 1. So you just be left with 1 over 1 minus r. Okay? Now, however, if r is greater than 1, so let's assume r is, say, 5, then you're raising a number that's greater than 1 to a really high power. So that means this thing that was 0 before now it goes to infinity. So that it goes to infinity. So what do? We can now write our formula for geometric series. K from 0 to infinity of AR to the power of K. So if R is greater than or equal to 1, we know that it diverges because this fraction goes to infinity or it becomes 1. So it diverges if R is greater than 1. And I'm going to say it's greater than or equal to 1. And it goes to 1 A over 1 minus R if R is less than 1. But what I'm going to do is that I'm going to consider the case where R is positive or negative. So for that reason, and if it doesn't matter if R is positive or negative, we're going to get the same answer. So let's just make the absolute value of R here. So this is a big result that I want us to remember. We're going to be using it a whole lot. How about I make it a little larger? Big result. Okay. Put it in red. So this result only applies to infinite series. It doesn't apply to partial sums. All right. So let's do some examples. All right. So we want to evaluate the geometric series. And if it diverges, we say it diverges. So this is the first one. Summation K from 0 to infinity of 1.1 to the power of K. All right. So if you look at this, compare it to A R to the power of K. So this means that our A is just 1 and R is 1.1. Okay. Now remember, if we have that, if R is greater than 1, it doesn't matter how much it is greater than 1 by. As long as R is greater than 1, the series diverges. So since we can say since R, absolute value of R is greater than 1, series diverges. Okay. Let's look at another example. Summation K from 0 to infinity of 3 times negative 0.75 to the power of K. Now again, we're comparing it to that. All right. So I'm going to use green this time. Our A is 3 and our R is negative 0.75. All right. So since absolute value of R is the absolute value of negative 0.75, which is 0.75, series converges. If a series converges, it's always good to know what it converges to. Sometimes it's impossible to tell, but in the case of the geometric series, we can tell because we have a formula. This is our formula, A over 1 minus R. So it converges to A is 3 over 1 minus negative 0.75. So the answer is let's see, what's the answer? The answer is, I'm gonna let you guys figure it out. I didn't do it. But it's quite easy. It's just 3 over 1.75. So figure it out yourself. All right. Let's see. Let's do one more. Let's do 3. How about the summation k from e to the power, k from 3 to infinity of e to the power of negative k. So we can begin by rewriting this as k from 3 to infinity of 1 over e to the power of k. All right? And then we can say this, our a is 1 and our r is 1 over e. All right? So this is the summation from k from 0 to infinity of 1 over e to the power of k minus summation k from 0 to 2. We've done an example like this before, to 2. All our formulas start from 0, but this example starts from 3. So we're going to go, our summation at 1 over e. We know that 1 over e is less than 1. It's definitely less than 1. So we can use the formula, so it doesn't diverge. We can use the formula r, which is 1 over e, over r, 1 over e, over 1 minus r, 1 over e. And then here we can use the formula for geometric series. We can use the formula for geometric series, or for geometric sum over here. But we don't need it. We can just list the terms. So this is 1 over e to the power of k also. So when k is 1, sorry, when k is 0, we have 1, because anything to the power of 0 is 1. When k is 1, we have 1 over e. When k is 2, we have 1 over e squared. So I want you to simplify this. This is your answer to this problem right here. This is the answer. Okay. Okay. All right, so there is another type of series I want you guys to think about. Okay, how can we deal with this series? This is not, we're done with geometric series. We're going to look at this kind of series we call telescoping series. All right, so let's look at some examples. The first one is k from 1 to infinity, 1 over 3 to the power of k minus 1 over 3 to the power of k plus 1. Well, it looks like the difference between two geometric series, but it's actually, but when you add them up, they look different. So think about this. This is like 1 over 3 to the power of 1 minus 1 over 3 to the power of 2. And then we can add, that's, so when k is 1, we get 1 over 3 to the power of 1 minus 1 over 3 to the power of 2. When k is 2, we get 1 over 3 to the power of 2 minus 1 over 3 to the power of 3. When k is 3, we get 1 over 3 to the power of 3 minus 1 over 3 to the power of 4, and so forth. Okay. So if we do this, we end up with something. Things are going to cancel out. This and this are going to cancel out. This and this are going to cancel out, and so forth. So if we begin by looking at the partial sums, so let's consider the partial sums. If you consider a partial sum, Sn will be 1 over 3 to the power of 1 minus 1 over 3 to the power of 2 plus 1 over 3 to the power of 2 minus 1 over 3 to the power of 3 plus 1 over 3 to the power of 3 minus 1 over 3 to the power of 4, and then you just keep going to the point you get to maybe minus 1 over 3 to the power of n plus 1 over 3 to the power of n, and then minus 1 over 3 to the power of n plus 1. Things are going to cancel out nicely. This is going to cancel out with this. This is going to cancel out with this, and so forth. Things are going to cancel out. So this partial sum right here is just 1 over 3 to the power of 1 minus 1 over 3 to the power of n plus 1. And remember that our infinite series, we've seen before that our infinite series is just a limit of the partial sum. So this is just going to be the limit as n goes to infinity of Sn. So it's the limit as n goes to infinity of 1 over 3 minus 1 over 3 to the power of n plus 1. As n goes to infinity, this part of the whole thing happily goes to 0. So our telescoping series is 1 over 3. So it's called telescoping because we have these numbers forming a pattern cascading between each other, and then at the end things kind of cancel out. They're kind of telescoping between each other. All right. So we're going to try another example. I want you to try this example, and then I'm going to give you a hint. This is example 2. How about summation? Let's look at a summation k from 1 to infinity of 1 over k times k plus 1. My hint is this. My hint is, not hint. We want to break up or use partial fractions. Use partial fractions to split 1 over k times k plus 1. After you use partial fraction to split it, then you can apply the same method we applied to number 1. Okay, so if you do this well, you're gonna get an answer. Your answer should equal 1. Okay, I think I'm gonna stop here for this section, and we'll talk more about it in class if you have questions.